Hi, in this demo, I will show you how to exploit buffer overflows and format string vulnerabilities. This is a well-known topic, of course, but this particular binary that I'm going to show you has some interesting characteristics. It has format string vulnerability as well as buffer flow vulnerability. Moreover, the address space layout is randomized. And then we also have the stack canary enabled. So whenever we try to overflow the buffer, the program will crash. So we will not be able to overwrite the return address, for example. Given such hurdles, I will show you how we can actually overcome in certain specific scenarios. Let's get started. So we are given a binary. Actually, in this case, we are also given the corresponding C code. The goal is to be able to call a backdoor function called hackme. So we need to construct some payload and then pass the payload that will eventually call the hackme function. So let's directly get into the code and see the structure of the C code and then the binary code. Okay, let's start with the C code first to get a high-level overview of what is there. All right, the first thing we see here is that we see hackme is here. Let's see whether anybody's calling hackme, first of all. Luckily, nobody's calling it, but our goal is to call hackme. How do we do that? We need to find is there any vulnerability inside? Okay, well, there is an echo function which is having a buffer and has the gets and printf. Gets is a vulnerable function in the C language world. It doesn't check the input buffer size, so we may be able to do buffer overflow using gets. Let's get started and see whether we can run some vulnerabilities there directly or exploit some vulnerabilities. Let's see. FMT is asking some inputs from us. What happens? Okay, stack is smashed. That means there's built-in production. We can't easily perform buffer overflows. Okay, buffer overflow attacks. So let's look at the disassembly of this particular code. I prefer to use the AT&T syntax, AT&T, and then let's clear the screen. Let's look into the echo function. Disassemble echo is better. On the side, we would like to keep the C code so we can look at the structure of the C code as well. Okay, so the echo function is taking the buffer and then eventually calling the gets function. So let's try to map this get printf puts here. Should be easy. It's not a long binary. Okay, so here is our printf. The first printf is here, and that's mapped here. Okay, and then we need a gets. So where is it? Here is the gets here, and here is the printf. Here puts here read payload over here. So we can map. The stack canary is being actually validated at the end. That's the reason why our stack smash attempt was detected. You know, here it is. Here it is. As soon as we cross the boundary of the buffer size, something is checked. When the program is about to return, when the echo function is about to return, we were caught. Okay. The reason why we were caught is that there is something called stack canary, which is placed at this particular location. This is a register name, and that particular value is compared against the value stored on the stack. So if somebody performs stack-based overflows and exploit stack-based vulnerabilities, usually the stack check fail will direct the problem. So in order to exploit this problem, we need to be able to carefully trick this logic. So what I'm going to do is somehow guess the correct value of the stack canary. In order to do that, we will leverage the other vulnerability. The other vulnerability I mentioned is the printf function, which is basically printing out the input buffer, right? Whatever the buffer was passed in is sent back to the user. So we can combine buffer overflows with format string vulnerability to be able to derive the stack canary value and then eventually trick this particular logic. And I will show you the details one by one. Okay, so let's get a feel for the format string vulnerability also. I'm not going to give a detailed overview of how stack is organized and how format string vulnerabilities actually work. That's beyond the scope. I will just focus on solving the problem. Okay, so let's continue this. Okay, let me just print some numbers and show you what is there on the stack. Some value is coming from the stack. We don't know what it is at this point. And let's continue exploiting this further. 6, nothing happens. Let's try 7. I'm browsing the stack, but oh, here you go. The AAA, that is basically what we typed in, is reflected here. 414141. That's basically the format string vulnerability is in action now. Most likely our A's are getting reflected as 414141 in hex. So we know that the format string is actually at the 7th position. Now we can traverse the stack and find out where is the stack canary. So let's do that. I have already done that. In the interest of time, I will directly show you that the 15th location is the stack canary. Let's run it again and it will change. That's the purpose of stack canary. It has to change. Okay, as you can see, it's changing. All right, well, it doesn't change all the bytes. Only the 3 bytes are changed. The let me clarify that. One of the bytes, 00, it will remain always 00. So the 3 bytes are actually randomized. Okay, but the question is, how do we guess all the 3 bytes correctly? Well, we don't have to guess it because our format string vulnerability will allow us to traverse the stack. We know exactly what the current stack canary value is, which we will leverage when we exploit this buffer overflow problem. But let's look into the read payload for a moment. So the read payload is actually an interesting function, small function. Very quickly, I will summarize what it is doing. It's reading data from a particular file. This is the particular file. It is actually asking the user how many bytes should I read from the file. Okay, and that many number of bytes are read into this buffer. So who is passing this buffer? Well, our buffer is passed by the echo function. That means this is a vulnerable variable, right? This is a tainted variable because we tell how many bytes to read from the file. And then if we are careful in the way we construct this particular file, this is a binary file, that's the reason we put B here. We will be able to trick the canary checking logic and exploit the vulnerable buffer overflow in particular. Okay, let me try now to show you how do we construct the payload. Okay, in order to construct the payload, we need to understand the stack layout, of course, which is easy to do in our case because it's not a large binary. So I will disassemble the echo. Okay, let's look into the gets function. Okay, the gets function needs one argument, buffer, right? So where is this in assembly? Here is the gets function. Here is the push statement. That means it's pushing the argument to the stack, on the stack. And then we can get the value of the buffer. How do we get the value of the buffer? Well, if you look at this release statement, which says CBB minus 2C. Well, what is 2C in hex to decimal? 2C is 44 in decimal. That means EBB minus 44 will have the address of the buffer. Okay, so if we can override 44 bytes, we will reach EBB. That's the whole purpose. And then another 4 bytes to corrupt the EBB, another 4 bytes to corrupt the return address. In total, 52 bytes. Okay, so let me annotate here. EBB minus 44 is the address of the buffer. Okay, that's the first point. That means fill 44 bytes to hit EBB, right? Another 4 bytes, fill another 4 bytes to fill up the EBB because it's a 32-bit architecture. And then finally, fill 4 more bytes to reach the return address. So our payload must have 22 bytes to successfully replace the return address by the address of the hackme function. Okay, so that's the key. The question is now, how do we fill up the canary? Because the canary will stop us. The canary check logic will stop us. We need to figure out the value of the canary and the position where it is, right? So if you look at it carefully, I think we can now move this to somewhere else. Okay, I'll keep it here. And then I'll show you where is the canary. The canary is EBB minus C, which is EBB minus 12. Okay, so what we have to do, we have to fill up the buffer first, 32 bytes of buffer, and then fill up the canary value. Okay, so we need to fill up the buffer, fill up the canary value, and then fill up the gap to reach the EBB, and then reach the return address. Basically, that's all. Okay, so I did put together this payload that I will walk through with you. Okay, now let's clear all the drawings, clear the screen. I will be now running the program, and the program is asking us to input something. We need to fill up, we need to actually find out the current canary value. So the current canary value is this. Okay, now we need to generate the payload, right? So I have this little Perl utility which will help us. So we need to fill up the current canary value. What is this? 00AC. This is Little Indian architecture. That's why I write it in the reverse. CAC0. Okay. Okay, so let me explain the structure one more time. So we have to fill up the buffer of 32 bytes, just because that's how the buffer is declared. And above the buffer was the canary value based on the assembly layout, assembly stack layout. And then we need to fill up 12 more bytes to reach the return address. That's why I fill in some single character. You can pick whatever character you like. And then I replaced it by a return address. So we need to be able to find the return address. The function that we want to call is the, let me check the function's return address, gdb minus q. I'm sorry. I need to start the set disassembly minus flavor AT&T disassemble hackme. So I need to get the address of the hackme function, which is this. ASLR is turned on, but usually the address of code region is not randomized, so we can leverage that, and we can just replace the return address by the address of this particular function. Okay, what I have placed here is the address of the another function, main message function. Actually, we can run it as it is now first, and then we will run the hackme function. Okay, so we have the payload. So all I have to do is just generate the payload, and then override it into this particular file. Okay, so now how many bytes should we ask the program to read from the payload file? Well, we need to read 52 bytes because 44 bytes to reach the EBB, and then another 4 bytes to fill up the EBB, which means 48, another 4 bytes to overwrite the return address. That's the layout I explained earlier. Okay, so surprising, we did see this message being printed out. Where is it coming from? It is coming from our program, and there is a main message which is not called anywhere. If you look at it, nowhere is called, but our payload actually was structured in a way that after calling the echo function, when the read payload was called, we overrode the return address of the echo function, and we eventually managed to call this particular main function, which has an interesting message, main message, that resolve the compiler warnings and overflows. If you compile it again, I'll show you after I finish the demo, you will see some interesting warning messages that I have excluded. Okay, I have ignored rather. Okay, so let's run the hackme now. How do we do that? We need to find out the current stack canary value. Okay, what is the current stack canary value? It is 007D 7D 4F 49. Okay, so let me double check. 49 4F 7000. We are good to go. And then let me use the address of hackney function instead of the main message function. So it is 86 and 0408. So we are good to go. So let's run it again. And ask this program to read only 52 bytes from our payload file. By the way, if you wanted to know what is inside the payload file, which is exactly the same thing that the Perl program generated, we could use this. And we can see all of the characters here, nicely shown. All of these. Let me clear this and show you one more time. Our bunch of A's, and then the current stack canary, that's what you're seeing here, and then bunch of B's, and then the return address, which is the hackney address. Okay. Now we are good to go. Hopefully this time we will be able to reach the hackney function. Yep. I thought the stack canary value will protect me. Well, let's see what this is saying. Yep, I thought this. And the segmentation fault, we should not worry because there is no return statement or exit here. That's why it's not in a good state, but that doesn't matter. We were able to reach the function that we wanted to reach. A couple of interesting points worth noting. We have 0, 0, but we can overcome that in this case because 0, 0 is happily accepted by gets function. Usually string function will not accept that after the first 0, 0. The string copy function will not accept that. That's not a problem in this case. We can overcome that. Also, one more thing is that even though the stack canary is there, we were able to overcome the logic. The way we overcome is we actually read the correct value of the stack canary and fill the buffer so that the logic that is actually checking is kind of tricked. What we did is that if we look at the last few lines of the echo function is these 3 lines, or rather these 4 lines are interesting. EBB minus C, if you remember, was the original stack canary value placed at runtime because of this statement, right? These 2 statements. What we did actually, we overwrote EBB minus 12 by the correct value, and above that we went and replaced the return address. So the stack check fail thinks that we were nice users, but actually we were very bad users. We crossed the limit of the buffer and overwrote the return address. Okay, that's pretty much it. And I just wanted to summarize with a small note here. You have to play a little bit to figure out when your input is reflected. That's part of the format string vulnerability challenge usually. And then we need to figure out exactly where the stack canary is in binary at runtime. And then we need to figure out how far is our buffer related to the EBB, how many bytes should we ask the program to read from the payload. Otherwise, we will not be able to reach the return address. Although my program is kind of local, meaning the user is actually a local user, there is nothing specific to this particular program. You can actually exploit this remotely, meaning if instead of reading the payload from the file, you could have been reading it from a socket. And instead of using the printf, it may be using write to a socket or something like that. So the remote user would be able to sort of browse the stack layout remotely and reply with a new payload that has the current stack canary value and can trick the logic. So to sum up, this is the payload architecture we talked about. 32 bytes to fill up the buffer, 4 bytes to fill up the canary value, and then 12 random bytes, in this case I just used B, to reach the return address, and then replace the return address by the address of hackney. So all in all, something like this was what I put it in the Perl or whatever script we like. And then we got the payload, and we got the program to change its intended control flow into something that the hacker wanted. All right, that's all. Thank you very much for watching.